Hi everyone, today we want to talk about spectral graph theory. Now let's consider one example. Here is a map from southeast part of the United States. Suppose I want to drive from Atlanta to Miami. To make this problem simpler, we will only choose those highways as a path. So here is a simplified map, where those highways are the edges and places connected are the vertices. Now, suppose the highway between Atlanta and Tampa is under construction and no car can pass. In this case, we can still drive to Miami by choosing another route. However, if the highway between Jacksonville and Daytona is also closed, then there's no way to go to Miami. In other words, the map is separated into two parts and there's no edge between them. Of course, we never want to see these things happening. To evaluate this kind of property of a graph, we will have a formal definition for this. And that is edge expansion. First, let's look at the part in the red box, which means for each cut, we can define a ratio, which is all edges that cross two parts divided by the number of vertices in a smaller part. And the edge expansion is the minimum value of all possible cuts. Obviously, in the traffic example, in order to make the whole traffic system stable, we want to maximize pi g. However, the bad news is that the exact solution of calculating pi g is NP hard. But instead of calculating exact value, we can have a bound for edge expansion. But before talking about the algorithm, I want to introduce the Laplacian matrix. First, let's look back to the previous traffic example. Laplacian matrix is calculated by degree matrix and adjacency matrix. Degree matrix represents the number of edges each vertex has, and adjacency matrix marks whether two vertices are connected by an edge. For example, row 2 and column 3 is -1 because vertex 3 and the vertex 2 are connected. Therefore, the degree matrix must be diagonal and the adjacency matrix must be symmetric. Then we can use the Laplacian matrix to get a bound for edge expansion. However, we will need a normalized Laplacian matrix for this. To get a normalized one, we will multiply the original Laplacian matrix with the inverse of the degree matrix. Then the second smallest eigenvalue is called algebraic connectivity. As the name suggested, a high connectivity means the graph is better connected. Then the corresponding eigenvalue will also suggest the sparsest cut of the graph. We can sort the entry in the eigenvalue and separate them into two parts. Then we can find the smallest edge expansion by trying different ways of separating. This algorithm is also called Fiedler's algorithm. Most importantly, Fiedler's value gives a bound for edge expansion, and the proof for Cheeger's algorithm is very complicated, especially the upper bound, and given with the limited time, I will not elaborate here.
Now let's see a novel clustering algorithm based on Laplacian matrix called spectral clustering. It contains two steps. First step is to use the data points and the similarity between them to build a graph on any given dataset. In the constructed graph, each node is just a data point, and each edge weight is given by the similarity between them. And it is common to use a Gaussian kernel to compute the similarity. In the formula, Wij is simply calculated by the Euclidean distance between two nodes. Another way is to connect each point with its k nearest neighbors. In step 1, we construct the graph given the dataset. Then step 2 uses Laplacian matrix to do clustering on it. It basically contains 4 steps. Compute the Laplacian matrix L, compute the first k eigenvectors of L, combine k eigenvectors to represent the data points, and use a traditional k-means algorithm to do clustering. As can be seen in the figure, spectral clustering obtains a better result on clustering two circles. Also, the algorithm is easy to understand and code. It is just some linear computations. Regarding the insight of research, there are mainly two promising and popular directions which would need us to explore next. First, it is widely used in graph convolutional neural networks because it is a key step for approximation of graph convolution. Here are three work about Laplacian matrix in GCN. First, it can be used in document classification with graph convolutional networks. As can be seen in a formula, in a graph of citation network, A here is Laplacian matrix, and the result of classification is just given by the multiplication of A and several other components. Also, it can be used in drug discovery. The figure on the right shows the residual Laplacian matrix, which just adds some special connections in a matrix. Third, some work focused on matrix approximation, such as Chebyshev's spectral CNN. Second, it is also widely used in clustering, especially combined with deep learning techniques. Here are several directions about clustering. First is deep clustering. As can be seen in a figure, left part is the pre-trained deep neural model to learn the representation in the graph, and the Laplacian matrix is used to do the clustering on the right part of the graph. Here are, next page please. Here are three different work. First is spectral clustering in heterogeneous information networks. For instance, some authors proposed an algorithm to learn a similar matrix on heterogeneous information networks. Also, multi-view clustering, which contains different resources, can leverage Laplacian matrix. Last but not the least, image segmentation can be regarded as graph cutting, which could solve by Laplacian matrix. And this technique is also popular in medical domain. That's all. Thank you.